All right. Hello, everybody. Welcome to Saturday Morning Astrophysics here at Purdue University on live broadcasting to the entire world. We've got people coming in from a bunch of different places across the world, so we welcome you. Thank you for joining us. Today's topic is going to be a very highly requested topic. It's one of the most fascinating and mysterious topics in the universe, and it is black holes. Everybody loves to learn about black holes. We will be doing an activity where we calculate the mass of a black hole, it's kind of a crazy number, but we'll get to that. We have a panel of TAs with us here today, and we have two very awesome speakers. We have Dr. Dimitrios Giannios from Purdue University, and we have Michael Damalakis. He is a PhD student here at Purdue. He works with Dr. Giannios. Do you guys want to introduce yourself real quick?
Hello, everybody. I'm Professor Giannios from Purdue University. I'm doing research in theoretical astrophysics, and today's topic is very close to my heart because that's what I have been working on the last 20 years or so, and it's about black holes, how these mysterious objects shine and produce all these amazing manifestations that we see in galaxies, in galactic centers, in faraway galaxies.
Hi, everyone. I'm Michael. I'm a fifth-year graduate student at Purdue University. I'm working with Professor Giannios in theoretical astrophysics, and I'm studying phenomena in the universe that are very energetic, that produce a lot of energy, a lot of light. And these things can be like death of massive stars, things that happen at the center of galaxies, or collisions of stars. And in many of those situations, black holes are involved. So yes, this is what we're going to do today. We're going to talk about black holes.
Awesome. Thank you guys so much for being here, and thank all the students for being here. My name is Amelia Binau. I am an undergraduate here at Purdue University. I've been working on dark matter physics while I was an undergraduate, and I'm going for my PhD next year, so that's cool. Who knows what a black hole is, or who can describe what a black hole is? All right. And it looks like Isa knows. Isa, you want to go ahead and explain?
Yeah, well, I would say a black hole, based on what I know, is like just a lot of matter, a lot of mass in a tiny little space. So that makes it really dense.
Yeah, very, very dense. In fact, I think infinite density at a single point that kind of warps space-time, but we'll talk about that. Yeah, that's a good description. Does anybody else have anything else to add?
I do.
All right, Samarth?
It's an area where there's like so much gravity that not even light can escape.
Yep, that's a perfect description too. They're so dense. It's a disruption of space-time to the point where there's so much gravity that light itself, which is the fastest moving thing in the universe, cannot even escape the gravity. Yeah, that is correct. Yep. All right. So two very good answers. I think we'll move on to Dr. Giannios's deep dive into the physics of black holes. So, yay, we're excited. Let's go.
And we can start with Michael to give us some introduction on black holes.
Yes.
Then
sorry.
I can
Michael
tell you
starts.
all about how to measure their weight.
Let's talk about black holes. In my opinion, black holes are the most fascinating and mysterious objects in the universe. The more we study them, the more we realize that we don't know much about them. So black hole is an area of extremely strong gravity, and the gravity is so strong that nothing can escape from it, not even light. So it affects everything, matter and light. Tell me, can we actually see a black hole?
We've got some answers in the chat here. I see no, because light can't escape from Matthew.
No, we cannot see black holes, because light cannot escape. That's why also they're called black. And we can also see around the black hole and not the actual black hole. That's very correct. Since we cannot see directly the black holes, that is my next question. Who knows now how we can observe them indirectly? What can we see around the black hole that, yes, after we observe it, we can say, okay, there has to be a hole there.
Well, I think we can see like the deformation of light around it, like because light, like even if it's not being absorbed, if it's not like close enough, like its path will be like deviated.
Yes, excellent. That's like I see like and we can see the stars that are affected, and we can also see the matter. So yes, Matthew said the accretion disk. I wasn't planning on using this terminology, but basically we can see the matter that rotates around the black hole. Yes, what we actually observe is the effect on nearby matter and light, as you all said. So let's start with one of the examples here. In this image, in the bottom left, we see the giant elliptical galaxy M87. So this galaxy is huge. It has trillions of stars. It's very bright. It looks like many other elliptical galaxies, but then we notice something weird going on there. There's something interesting in this galaxy. Does anyone can tell me what if we see something like weird in this galaxy?
There's like a blue thing.
So yes, there is that blue thing coming out of the center of the galaxy. So let's zoom in a little bit and see what's going on there. The blue thing that you see in the left image now looks like that if you zoom in. Yes, you can see that something weird is going on at the center of this galaxy. You see a lot of gas, and then you see also gas moving out of the center of the galaxy. So yes, in that case, we can guess that something very massive is at the center of the galaxy, and this has to be a supermassive black hole. Yes, that's one of the ways that we can indirectly observe a black hole. And let's move to another example. That's also very interesting. Who knows to tell me what we see now on the image at the bottom right?
It's two stars that are being affected by the black hole because their orbit is changing.
Yes, these are stars specifically at the center of our galaxy. From their orbits, we can figure out again that there is a supermassive black hole at the center of our galaxy. Their orbits behave in a very specific way that there has to be something very massive at the center, otherwise they won't behave like that. So we know that these stars behave the way they do because there is a supermassive black hole at the center of our galaxy. These are their orbits around the black hole. So they're not close enough to be drawn towards the black hole, but they're still relatively close, so they manage to orbit the black hole very quickly. So their orbit is around 10 years. For comparison, our star, the sun, takes 200 million years to orbit around the galaxy. These stars move extremely fast. Yes, they move extremely fast, and yes, their orbit is very, very short. Also, the galaxy, the galaxy that we see on the left, has the gas that rotates around, that is around the black hole. After while it falls towards the black hole, it gets to very high temperatures, like millions of degrees, and it emits a lot of light. It produces a lot of light, and this is what we actually managed to see. We see the light that's produced by the heating of this gas.
Martha asks, what is the gas made of?
Gas could be made of hydrogen mostly, and then we can also have dust. But yes, I would say it's mostly hydrogen. I think we can move to the first breakout activity.
My name's Grace. I am a junior in physics and astronomy here at Purdue University.
Yeah, I'm Thomas. I'm a sophomore in physics and astronomy at Purdue.
So what we're going to do here is we're going to take our wine glasses and we're going to kind of simulate what it's like to look at a black hole and how black holes kind of affect light. This isn't going to be the exact same process, obviously, because when a black hole bends light, that is due to gravitational attraction, versus when your wine glass bends light, it is going to be due to refraction in the glass, but it will look very similar. So what you guys are going to do, you're going to pick it up, make sure not to break it, and you're going to kind of use it like a telescope almost. I would say just put it up to your eye, and if you have a flashlight, point the flashlight towards it. Otherwise, you can just look up to any bright light source, like if you have a light in your room or just anything at all. And as you move your wine glass, you'll kind of be able to see that the light warps around the base. Are you guys seeing that effect at all if you're pointing that at a bright light source? Maybe like move it back and forth to get that effect. So that would kind of give you an idea of how, because these black holes are so massive, this only happens with the most massive objects in the universe, how as light from background objects passes by a black hole, it warps and bends it from our perspective. Another way you could also view this phenomenon, I don't know if you guys printed out like that deep field image, or if you even have a lined piece of paper. If you just place it down on top of your piece of paper, you can move it back and forth and see how it bends the stuff below it. And that's going to be a similar effect. This effect is actually called gravitational lensing. It's a really, really cool thing, and it's very, very helpful for a lot of scientists.
I'm just not sure, like, where does this apply? Like, in space? Like, what would be the glass and what would be, like, I guess the light and the black dot could be the black hole, but what would be like the glass?
That's a great question. So the black dot could be another black hole. The black dot could be anything. I called it a black hole because you can use the printout that we use to kind of just pass the glass in front of that image. But the glass itself is a massive object like a black hole. It can be a massive cluster of galaxies as well. In fact, the first James Webb image that came in was a massive galaxy cluster that had this similar effect going on, the gravitational lensing effect going on. It's anything with enough mass to distort space-time.
Who can tell me what we did now in this breakout activity?
We looked through a wine glass to simulate the warping of light around the black hole.
We used the wine glass to see how light bends close to a black hole. Can we say that black holes are wine glasses? No. The mechanism that bend the light in those two situations are very different between the glass and the black hole. In the case of the black hole, what is it that is responsible for the bending of light?
Gravity?
Yes, it's the extremely strong gravity close to the black hole that's responsible for the bending of light. Of course, part of that light that bends manages to escape and reaches our telescopes. Part of that light also, if it gets very close, it can cross what we call the event horizon of the black hole. Who can tell me what we call the event horizon of a black hole?
The event horizon is like an invisible line where things can't escape from that. Like, once they pass that line, it can't escape anymore because gravity is way too high.
The event horizon is what we call the point of no return. Once something, whether it's matter or light, crosses this invisible boundary, it cannot escape. As you can see in the image on the right, this is again the galaxy M87 that I showed you before, at the center of this galaxy. And then we see this jet of matter and the gas around the center, and then we can zoom in, and then we can see this jet of matter even better, and then we can zoom in again. Like we kept zooming in, but until very recently, we hadn't managed to see a black hole at the center. So that was the question. How can we use the bending of light to see a black hole? So we used the help of computers to help us understand how a black hole would look like. So let's start with an illustration that has been, who can tell me what we see here?
A black hole.
Correct. So we see a black hole. Where is that black hole, like in this image?
In the center of it.
Who can tell me what is that thing around the black hole, maybe?
Well, it's like light and matter and things like orbiting.
Yes, very well. This is a disk of matter that rotates, that orbits the black hole. As we said before, if you have a black hole by itself, we cannot observe it, never. So we need to have something around the black hole to be able to observe it. So in that case, we believe that at the center of galaxies, we have a disk of matter. This is very hot, it emits light, so this is what we want to observe. Who can tell me now this disk of matter, why does it look like that?
It's a disk, but because the light gets bent, you can see the disk from both the top and the bottom, even though it doesn't actually go around those ways in that shape.
Very good answer. So this is the light from the far side of the disk, from the part of the disk that's behind the black hole. This is the amazing property of like bending of light that we're talking about. You can actually see what's going on behind the black hole. So you can see here the top part of the disk, on the top part of the image, that is, the light is bent and reaches our line of sight. And you can also see the bottom side of the disk on the far side of the disk that also managed to reach our line of sight. Because of the way that light works in those situations, we don't actually see the black area that is the event horizon. We see a relatively larger area, about twice the size of the event horizon, that we call the shadow of the black hole, which you can think of it as literally the shadow that the black hole casts, like when light travels around it. And another thing that I want to point out is that like a thin bright ring close to that shadow, and which is also close to the event horizon. This is what we call the photon ring, where photons that manage to rotate around the black hole several times before they escape. This is a very thin, bright area, and this is also like part of what you expect to see in observations. What we expect to see is kind of like a ring of light, something dark in the middle, at the center, which is the shadow of the black hole. And then we expect to see also like a brighter ring on the outside, which is the disk of matter that emits light.
After this excellent introduction from by Michael, we have all the background we need to understand, and you will be the scientist now. You will put a giant black hole, a supermassive black hole, on the scale and measure its weight. I believe we have all the tools now to do this experiment. Now, as Michael has explained, if there is hot gas in the form of plasma close to a black hole, this is shining. It's getting so hot, in fact, that it's much hotter than the surface of the sun. The temperatures there of the plasma can be millions of degrees, can be 1,000 times hotter than the surface of the sun, and produce a lot of light. And in fact, what we see as a ring, or that's what the theory predicts, is that what we see as a ring of light is in fact the gas that is behind the black hole, and its light gets focused towards us. The black hole acts like a huge magnifying glass. Now, the size of the ring has very important information. It can tell us something about the mass of the black hole. The general theory of relativity predicts that the bigger black holes have larger rings. The expression that relates the diameter of this bright ring and the mass of the black hole is written over here. The mass of the black hole is proportional to the diameter S of the ring, and I have some units here to guide you. This expression essentially tells you that if you have a black hole of 1 solar mass, if the sun collapses to a black hole, then its ring will be actually tiny. It will be just 15 kilometers, around 10 miles or so. It's just the distance you can cover with your car in a highway in 10 minutes or so. It's a tiny distance. And that means automatically that these rings are extremely hard to observe. These black holes are in faraway galaxies, and they are fairly tiny. How could we even hope ever to see such a tiny object in the sky? Now, let's try to get a bit of understanding how big objects appear on the sky. What is their angular size? By angular size, I really mean how big is the object, meaning how many degrees it appears on the sky. And actually, that goes to as a question to you. What do you think determines the size of an object in the night sky?
Well, I would say it's like how far away they are from us and what's their like real diameter. Both of us, yeah.
Yes, that's correct. Both of these factors are important, how big the object actually is physically and how far away from us. So what do you think? If an object is far away from us, does it appear bigger or smaller on the sky?
It would appear smaller.
Of course, smaller, right? If you move something away from you, it appears smaller. So the size, the angular size of an object is proportional to the size, the physical size of the object, and inversely proportional to the distance d. The expression that gives us the angular size of the object theta is proportional to s, the diameter, inversely proportional to the distance. And as an example, let's see how big is the full moon in the night sky. If you actually, can you guess what is the size of the full moon in degrees in the night sky?
I think it's half a degree.
That's exact. It's around half a degree. But let's do the calculation here. Well, the diameter of the moon is around 3,500 kilometers. and the distance to the moon is approximately 380,000 kilometers. If you put these two expressions to these quantities in the equation here, you get half a degree. Just to understand a bit better, how big is this object of a half a degree? Suppose that the moon is a dime. So you have this coin, you have a dime, and you want to place it far from you so that it appears just as big as the full moon in the night sky. And that's actually another question to you. Take a dime and you put it away from you. How far away should you place it so that it looks like the full moon? So I believe you all got it right here. Yeah, I see a lot of 1 meter answer. Mm-hmm. And that is absolutely correct. So it's 1 meter. So this dime, if you place it 1 meter away, that's the full moon, more or less is the size of your pinky. If you stretch your arm and look at the sky, that's the size of the full moon. Now, how about the photon ring from a supermassive black hole? How big would that be? How far would you have to put the dime away from you so that it looks the size of the photon ring from a black hole? I remind you the photon rings, of course, you don't have all the information you need to answer this question, but I want you to get a guess. The photon rings are very small, but how far away should you place the dime?
We're getting a variety of answers here. We have a few on the moons and a few a town 10 miles away, which is kind of interesting.
So is it a close call, but nobody likes Australia for some reason?
Yeah, for some reason. We've got a few more on the moons than we do at a town 10 miles away.
Well, guys, we have to put the dime on the moon. We have to throw the dime on the moon if you want to see it. So that is how small this ring is from a supermassive black hole. Throw a dime on the moon and try to observe it. Now, of course, normal people would give up on that hope, but scientists are not normal people. So they worked very hard to observe it, and that's observers. I'm a theoretician, so the observers are the real heroes here. They turned the whole Earth into a giant telescope. They put radio dishes, which detect radio waves, which is light, all over the globe, from the South Pole to Hawaii to Greenland. And they looked at the same source persistently for a few years. They collected a lot of light and combined all this information from this center of a galaxy to try to see the tiny structure at the very heart of this galaxy. And after several years of observations, they could zoom in. As Michael mentioned, this is the picture from the large scale for the whole galaxy of the gas in the center of this galaxy. And then we can zoom in and see the structures closer to the very heart of the galaxy. Then we can zoom in, take this little box and expand it one more time. And then we see very close to the heart of the galaxy, to this supermassive black hole. Yet one more step of zooming in, take this little box now and zoom it in. And here is the ring. There is a dark region surrounded by a bright ring. For the first time, we are witnessing a supermassive black hole. And amazingly, it's exactly what the theory had predicted 100 years ago. This straight line here shows you an angular size on the sky of 20 micro arc second. Now, micro arc second is a ridiculously small unit. Take the degree, and do you know actually what is an arc second? Arc second measures angles. Do you have any idea how the arc second relates to the 1 degree?
So a degree is like 60 minutes, and a minute is 60 seconds. So it would be like 1 over 3,600?
Exactly. 1 arc second is 3,600 times smaller than the degree. Now, a micro arc second is an even smaller quantity by another factor of 1 million. Micro is like a micrometer is a millionth of a meter. The micro arc second is 1 millionth of the arc second. So the size of this ring is about millionths of an arc second, but it has been observed. And with the size now of this ring, and it's your task to go to the breakout rooms and calculate the mass of the black hole. Please come back to me with an answer. I want to know how big this black hole is.
All right, thank you, Professor. We will go to breakout rooms now. We'll be in there for 10 minutes, and we will work through the calculation of the mass of the black hole. So you're sharing. Oh.
Who has an idea about the first step that we should take for measuring the mass of this black hole? Oh, there's a question in here. I'll take a look at that real quick. Gravity is the weakest force. Why is it stronger in black holes? Ray, do you have an answer to that question?
I have to believe it is because of just how massive and how dense black holes are. Like, they're incomprehensibly massive. And I think that has to just alleviate the weakness of gravity.
So the first thing I think of doing is measuring the size of the ring and then comparing it to the 20 microarc seconds that we have.
We're going to measure it in centimeters or millimeters and then compare to the line at the bottom, which will tell us the number of microarc seconds in our measurement. Is that correct? I just want to make sure I'm on the right track.
Have you all had a chance to measure those values yet? Roughly, how many times bigger is the photon ring than just the 20 microarc seconds line that we're given?
About 3 times?
3 times? Okay. When I did that, I was getting a number close to 2 times, but we can stick with that too. I'll check my numbers again real quick. The way I zoomed in, I was measuring the 20 microarc second bar to be about 3 centimeters long. And then when I measured the photon ring, I was measuring about 6 centimeters long. Is that similar to what you were seeing, Hashini?
I measured the 20, I forgot what it's called, about 1.27 centimeters. And then like 7 centimeters for the photon ring.
So we can do the conversion factor. I personally am measuring the photon ring to have a width of about 40 microarc seconds. And that's the symbol that we'll use. So then we have that angular size in the sky, but what should be the next steps that we take to convert that maybe to degrees first and then to actually get the size and the mass? So what I'm thinking we should do next is we have this 40 microarc second size of the black hole. Then we're given a formula to convert that to degrees. That's essentially just to multiply that by 2.8 times 10 to the negative 10. So it's a really small number. So yeah, we can try that on our calculators real quick if you all have that. And then if anyone gets a number, then let me know.
Yeah, I got a number.
You got a number? Okay. What did you get, Ray?
I got 1.12 times 10 to the negative 8 degrees.
That's what I got too.
Oh, let's go.
So I measured 40 microarc seconds, which is this number here. And then when converting that to degrees, I just multiplied it by this number. And that's how I got this 1.12 times 10 to the negative 8th. And that's the same number that Ray was getting to. So that's good. So this is how many degrees our black hole is taking up in the sky, which is ridiculously small. But yeah, then there are more formulas that we can use to convert that to a size. And the most important thing is that we know this formula too, which is going to convert to the size from here. That only requires us to know this distance, but at the bottom here, we're given that distance is 5 times 10 to the 20th kilometers. So does anyone want to try doing that calculation on their own before I just plug the numbers in here?
So Gabe, just to make sure I'm on the right track, the very first equation where you have S equals d theta over 57, that d theta is given in the very last paragraph under the images, right?
D is given at the
Or
very
D,
last.
I'm sorry, right.
Yeah. And then theta is just going to be this 1.12 times 10 to the negative 8th number that we calculated here. So I'll start typing in some numbers. So I'll just say the S, or the size, is equal to D times, I can't really put theta in here, so I'll just put T for convenience. And then over 57. And then I might as well just say that this is equal to T right here. So now the only thing that we need is a value for D. That is equal to 5 times 10 to the 20th kilometers. Does that calculation make sense to all of you?
Mm-hmm.
Yes? Okay, great. So this is the actual size of the black hole. If it's that far away, we're measuring that angle, it's going to be 9.8 times 10 to the 10th kilometers wide, which is really, really large. So then how do you think we should convert this to the final mass of the black hole from here?
Well, I think we should look at our nifty formula sheet and see that we have an expression for the mass of the black hole given our size. So I think we should plug that value in, as well as the value for the mass of the sun.
Jeannie, what do you think? Do you agree with that? Or do you think we should do something different? Or
I agree.
Okay, cool. I see the breakout rooms are about to close, so I'll go fairly quickly on this. So if I just divide S by 15 kilometers, then if we multiply that by the mass of the sun, then we get the actual mass of the black hole. But then if we just divide by M sun on both sides, then S over 15, that's just going to tell us how many times more massive than the sun this black hole is. And when I do that, I get this really large number. What that really means is that this black hole that we're measuring right here is 6.5 billion times more massive than the sun. Isn't that crazy to think about?
It is crazy to think about.
Yeah.
So let's talk about what we got there. What values did we get?
You got 6.5 billion masses of the sun.
About half, or 5 to 6 billion solar masses, which is kind of a crazy result.
That's correct. So we got some brewing scientists here. Indeed, at the heart of that galaxy, a large elliptical galaxy, M87, lies a huge black hole of 6 billion solar masses. It's a monster down there. We suspected it's there, but now it's the amazing thing that we took a photo of the monster and verified by the size of the ring how big this black hole really is. The whole trip started 100 years ago when Einstein wrote down his equations for the general theory of relativity. What he wanted to describe is, for example, how the planets move around the sun, or how the satellites, the moon rotates, revolves around the earth. His theory is general, applies to everything that involves masses in the universe. Ended up to describe white dwarfs and neutron stars, and even the most amazing and exotic objects, the black holes. This solution of his equations called black holes was discovered 100 years ago, and for a long time scientists believe that these are not relevant for our universe, that these objects probably do not exist. Only in the 60s and the 70s, the scientists started suspecting that some of these objects we see in the night sky are some of these activities related to black holes. And the whole trip comes now back to close with this amazing observation of the very heart, of the very silhouette of a black hole. We have this supermassive black hole at a nearby galaxy with 6 billion times the mass of the sun. And the same technique has been applied very recently to the supermassive black hole of our own galaxy. That is a smaller black hole, but it has similar size in the sky, just because our own galaxy, the center of our own galaxy, is so much closer to us. And that has 4 million times the mass of the sun. So we have seen the rings from 2 black holes, one of in a galaxy far away, and one in the center of our own galaxy. And we have verified the general theory of relativity of Einstein. And I think I will leave it here so that we don't run too much overtime.
Can I ask a quick question real quick?
Yes.
In terms of how massive black holes are across the entire universe, was that a relatively large, medium, or small black hole that we calculated?
As far as we know, it's close to as large as it gets. We have suspicions that some huge galaxies harbor even larger black holes, maybe 10 billion or 20 billion times the mass of the sun. So there can be black holes out there that are 2 to 3 times bigger than what we have seen. This is a fairly large black hole. Inside our galaxy, we suspect we have millions of black holes that have mass about 10 to 20 times the mass of the sun. And these are from stellar evolution, from the collapse of massive stars. But we believe also each galaxy harbors a supermassive black hole at its heart, and this black hole can have mass from millions to billions times the mass of the sun.
In the Breakout room, I understood that astrophysicists and scientific people liked to measure those masses based on, or those weights, I don't know, based on the mass of the sun. Right? So the number we got, 6.5 billion, is that times the mass of the sun, or is that the real mass?
That is exact. The unit is the mass of the sun. If you are interested to know the mass in grams, for example, kilograms, then you have to multiply with the mass of the sun. It's something like 2 times 10 to the 30th kilograms. So it's a huge number with 30 zeros in kilograms on top of this 6 billion that you found already. It's just that we find it more useful in astrophysics to use the mass of the sun as a reference point.
Looks like we have another question in the chat. Matthew asked, how did supermassive black holes form?
That is a big mystery, Matthew. We still don't know the answer. We know that they are there. Whenever we get good data, we discover supermassive black hole. What we know is that they grow together with the galaxies. Large galaxies have larger supermassive black holes at the center, and smaller galaxies have smaller black holes. How exactly they grow together, we are completely at a loss. The interesting part is that the supermassive black hole, although it's such a huge object, it's not huge in comparison to the mass of the galaxy itself. Approximately, the supermassive black hole has mass 1,000th of the mass of the galaxy. The galaxy is yet another 1,000 times larger in mass in comparison to the supermassive black hole at its center. Another question I see here is how big is the one in our galaxy, and why is it in the center? The one in our galaxy has a mass of 4 million solar masses. The supermassive black holes in general lie at the very heart, at the very center of the galaxy. And the reason is more or less because the heavy objects sink to the center of the gravitational potential. There are interactions, they kick away stars and gas, and they settle in the very bottom, in the deepest of the gravitational potential, while lighter objects stay in the periphery. And that can take actually many millions of years to happen. So galaxies can merge, can collide, and their black holes can also come together and collide and settle down in the very heart of the new forming galaxy.
Malaika had a question here. What are wormholes then?
Wormholes are more speculative solutions of Einstein's equations, connecting distant points in space, making shortcuts in space that could allow fast travel. We are not aware of such solutions in practice, of such situations in practice in our universe, but they may well exist. So we haven't found a wormhole yet, but there are specific solutions of Einstein's equations. And I see one more question here for, can black holes grow over time? And when they grow, does the diameter grow as well? Yes, they do grow over time. The more gas that falls into the black hole, the bigger they get. And indeed, the diameter of their ring or of the horizon grows proportionally to their mass. As time passes, a black hole can initially be a few million times the mass of the sun, and by the age of the universe, by today, may have grown to billions of times the mass of the sun, more or less together with the galaxy. As the galaxy grows, the black hole grows as well.
How to visualize like how big this black hole is? Like they found 6 billion solar mass, but like how big this black hole is? Like
yes, that's a good question, and we got even a number in kilometers, right? Something like 10 billion kilometers, 10 to the 10 kilometers, something like that. And this is comparable to our solar system. You can think the distance from the sun to Pluto or some of the outer planets. System of the size of the solar system is more or less the light ring of the black hole. Can appear to us as something huge, but in terms of astrophysical objects, that's fairly small, in fact. It's a tiny part of a galaxy.
All right, Daniel is asking, would smaller black holes be stronger? So probably have higher gravity.
Well, that's a good question. Smaller black holes do not have stronger gravity in the sense that they cannot attract material from very far away. A bigger black hole can attract material from further away. But that's an interesting question because in a smaller black hole, the tides can be stronger, the tidal forces. If I throw you in a supermassive black hole, then you will cross the horizon and you will not feel anything. You will be beyond the point of no return, but your body will not feel anything until you hit the center. But in a smaller black hole, let's say of 10 times the mass of the sun, the tides are so strong that it will rip you apart before you even cross the event horizon. These tidal forces are like the tides we feel from the moon, where they pull more your legs than your head when you are falling to the black hole legs first. So if you are going to visit a black hole, go to supermassive one. And yes, it's stronger, exactly, the gravity, because we are really very closer to the singularity, and the tidal forces care more about the distance than the mass of the object. That's why the moon has the same tides on Earth, or larger tides than the sun, because it's so much closer to us. Although the moon doesn't have such a big mass, it has stronger tidal forces to Earth than the sun, just because it's closer. That's exactly correct.
All right, I think we have to wrap it up here, but you guys have very good questions, and there's a lot to explore with black holes. And if you want to learn more, there's tons of resources online. You can find books about black holes. You can probably contact one of us if you have more questions. Contact Dr. Cedarberg, or I mean, honestly, ChatGPT nowadays. You could type your question in there and you can ask it. It will probably give you a pretty close answer. Take that with a grain of salt, though. But thank you guys, Neil. Yeah, Thomas has Neil deGrasse Tyson's book on black holes, Death by Black Hole. So we'll wrap it up here. Thank you guys so much for coming and participating, and for all your awesome questions. Yes, thank you, Isa. You guys are really smart and inquisitive, and we appreciate that, and we appreciate your participation. So thank you so much, and have an awesome month until we see you again in our next Saturday morning astrophysics. So thank you guys.